I'm Roland Snooks. I direct the Architectural Robotics Lab at RMIT University. And today we're going to hear from distinguished Professor Mike Shear and Alex Walser, both from RMIT. Amelia Liu will be giving a demonstration of incremental sheet forming at the WAAM Hub. And then from QUT, we'll hear from Alan Burden and Muge Teixeira. So architectural robotics is the application of industrial robots to the fabrication and construction of buildings. But the key to this is the experimentation and integration of robotic fabrication techniques within design. So this is not simply about using robots to automate what we already do. This is about exploring what are the design implications of innovative fabrication. So how does this make the things we design and build different because we're using robots? So at the lab at RMIT, we've tested many different ways of using industrial robots within fabrication and architectural design. So starting with techniques that are relatively, let's say, traditional, like subtractive CNC milling. And then we've moved through techniques such as metal rod bending or forming of metal sheets through a process which is incremental sheet forming, basically pushing into a sheet of metal, or developing a series of ways of making custom extruders to extrude material from robots, looking at vision systems and the way that allows us to interface with volatile materials or with biological materials. But the vast bulk of what we've been doing recently is around 3D printing. And of course, often when we think about 3D printing, we think about these desktop or relatively small 3D printers, maybe making things at home or in the aviation or aerospace industries, sort of high-tech industries. What we're interested in is scaling this up and working out how we can 3D print parts of buildings. And so a lot of our work has been around using 3D printed plastics and then figuring out how we get those plastics such as polycarbonate through building codes and fire codes so that we can use them in as permanent parts of buildings. So our first time we've got this through building codes was this small meeting room in at Monash University. And then we've also worked on larger structures such as this installation for the National Gallery of Victoria. But plastics are inherently relatively weak materials, and so we're interested in the way we can reinforce those. So a lot of our work recently has been around printing what we describe as sacrificial formwork. So this is where we're printing thin skins and casting structural material back into them, and whether that's fiber reinforced concrete, or more recently we've been working with Boeing to work out how we can infuse carbon fiber into these 3D prints. And so here's an example of that we tested in an architectural installation recently in the Shenzhen Biennale in China. But the work that we've been doing as part of the IMCRC Design Robotics project has been shifting from printing in plastics to printing in metals and working in metals more generally. And so Alex will talk shortly about this in more detail, but we've been looking at a process called wire arc additive manufacturing, where we're effectively using a MIG welder to print metals in a very similar way to the way we've been printing plastics, and then looking at the way, what are the architectural implications of that and how we can start to scale that up. Okay, so now I'm going to hand over to distinguished Professor Mike Shear.
I work with Roland very closely, and the main work we are doing is try to take advantage of the opportunities provided by robotic fabrication. And because the kind of structure my group design is very complicated and intricate, with intricate details. So my team developed a very simple method to design these high performance lightweight structures. So the idea is actually very simple. If you want to design a better structure, you can start from any initial design, then gradually remove those unnecessary parts from the current structure, and what's left over would be a highly efficient structure, and also it looks very elegant and organic. And the technique can be easily linked with existing design tools like Abacus, Rhino, and other software widely used in the industry. I show you a very simple example of designing a structure, object hanging in the air. So we start from this square design domain. We want to know if we fix one point at the top and apply the gravity, what would be the best shape for these given conditions? So we can divide it into small grids. So these are called finite elements. And then when we do structure analysis, we will find the four corners have zero stress, which indicates that these parts are not efficient or unnecessary. So if we gradually remove those inefficient parts, we will see something evolving on the screen. Maybe it's a bit not smooth, but you can see the idea. So every time we remove those inefficient parts, and you get a new design. So that right-hand side is a design with all the unnecessary material removed. So then we improved our technique. So not only can we delete those inefficient parts, we can actually add material to these most critical areas. So the process becomes bidirectional, and the algorithm would be far more robust and efficient. I show you one simple example of using this bidirectional approach to design a bridge. So you give the loading on the deck, fixed 4 points at the bottom, and your initial design could be very simple, like a slab with 4 columns. And the rest can be determined by the computer. So it will gradually add material to those critical parts and delete. And the video is not running, but I show you the final outcome. So this is how it works. So adding and deleting simultaneously, you would get from a simple starting point at the bottom, you get an arch bridge with additional tree branch type of components. So the outcome is very organic, it's very elegant, although our process is very simple and it's based on mechanical rules. So we have used our technique, and we also have some practical projects in Australia, China. This is the footbridge we designed for Suzhou, China last year using our technique. This is another bridge. So the initial design is a circular tube. By applying our technique and remove those redundant parts, we can come up with this beautiful innovative structure, and it's lightweight and it's highly efficient. And we have developed a software called Amoeba. It's a link to Rhino Grasshopper, and it's doing all the computation on the cloud. And all the algorithm is based on our BSO technique. And I show you some of the results. So my student used Amoeba and design all sorts of things like this jewelry, chairs, furniture, and another student did design a table. So if you come to my office, I think Jared's seen this table in my office. These are all designed using our own technique. And some of my younger students designed high heel shoes for themselves, 3D printed. And this is a wooden pavilion. It's all designed using Amoeba software. And this is a drone. So the whole thing started from a material distributed everywhere. By applying our technique, we can get this design. The whole frame is 3D printed and it can fly. So the video is not running, but it flew very well in our campus. And this is one of the examples we used Roland's large-scale robotic printing and to print this structure. I just stop here. So this whole thing was printed using the robots in Roland's lab. Thank you.
Mike, thank you very much. And we'll now hand over to Alex.
So hi, my name is Alex. I'll quickly touch on how robots are being used in metal manufacturing, as Roland has mentioned before, and the work that we have been doing as part of the IMCRC. So I think one very promising technology is the additive manufacturing of metal components. And there's a few processes out there for kind of 3D printing. Additive manufacturing is maybe just another term for 3D printing. And the one that we specifically are looking at is the one using wire-fed welding system. So how does this actually work in detail? Basically, a MIG welding torch that is commonly used in industry for welding kind of single beads. It's used on a motion system such as a robotic arm or gantry system, and the torch is traveling along a pre-computed path. And by doing so, it's actually stacking up these kind of layers. And this, as also Mike mentioned before, allows you to compute or to put material only where required. And you can make very complex, very strong components by using only the material that is needed according to the prior calculation. So what we've been doing at RMIT is basically developing, like taking these existing technologies like this MIG welder, an advanced system, existing robotic arms, and we develop workflows where then a user, a designer, a fabricator, a company can use and can fabricate from a given design. It can calculate all the stats, let's say material estimates and time estimate of printing, and it can automatically fabricate these parts. So we've been producing a few of these components. They are quite rough, so they are kind of unprocessed, but this one shown on the right side, done in collaboration with University of Wollongong. This has been sandblasted and coated, but you could also imagine applying any kind of deep burring or lineaging process to this part, or even milling. This is often seen. The second fabrication workflow I want to touch on is the formative processes of incremental sheet forming. In incremental sheet forming, a sheet is basically kept in confinement, and a robot or a system with a tool is traveling along this sheet. And by doing this incrementally, you can step down and you can create very complex geometries from an initial 2D sheet. In this case, again, and Amelia will give a demo just after me, we developed a workflow where, again, you can take the design, you can set up your robot system, you can simulate it, and you get also the estimates for time. And of course, we verify these results with the fabrication. And we also have done this in remote collaboration during this kind of lockdown times. So we were basically streaming and controlling robots from Melbourne to Brisbane and back. The next steps ahead, as mentioned before by the other panelists, is integration of machine vision into these systems. Also the integration of optimization of topology and shape to apply. As architects, this is interesting to apply these new technologies and explore what they could mean for architectural expressive facades, but also making these tools available for artists and designers. Look, if you have any questions, do not hesitate to reach out to us or post a question in the Q&A. Thanks, and I'll hand over to Mia. Thank you.
So as you mentioned, we did incremental sheet forming as a COVID project, essentially, between RMIT and QUT here. So as he mentioned, it was all done purely remotely in that Alex was obviously in his apartment and he was stuck there for indefinite periods of times and probably still is. But we actually have some sample pieces of what the incremental sheet forming actually result looks like. So of course, this was a little bit experimental for us and it was a first time for us to do it in this way as well. But it came out really interesting actually. So you can kind of see in this one, we had a 1 mil step down, and you can kind of see each of the little layers. But we've put a pentagon on top, a cone on top of a pentagon in this example here. And the way that we've done it is we've actually used the robot that's behind me, which I'll bring you closer to in a second. But we've made a 3D printed little mount that's dapping tools. So they come in various sizes. And we've used the smallest one because we're actually using a UR10, which is that guy there, which was the same one that was used for the lineaging robot. Yeah, so we've used the smallest one being 5 mils, 5 mils in the tip here, purely because of the forces and things like that. And as well, the material that we used was only, I believe it was 0.3 mil thickness of flashing aluminium. That's what it's called. Yes. So what we've done is essentially be able to put these tools into this 3D printed mount onto the robot. And then what Alex and I have been working on has been generating grasshopper scripts. So I'm going to start moving us. Grasshopper scripts that let us control the robot. So let me share my screen. Here you go. So what we can see here, ooh, wrong button, turntable, crazy spinning, yes. So what we can see here is we actually, in order to do this remotely, we had to set it up we had to put a lot of thought into how we set it up essentially. So what we were able to do was essentially generate this digital twin. So we can actually see the artwork here that's been 3D modeled. We can see the robot on its little table that's there as well. And what we're able to do with this is actually, we can simulate so at this point it's actually running. These white lines are the ones that the robot is about to do. And we can actually simulate how the robot will actually move. So this has been incredibly handy for us to be able to actually test the physical setup and actually see how things are gonna happen, whether collisions are gonna occur, etc., all things like that. So I think the robot's actually stopped moving. Let me run one of the passes and we can bring you a lot closer to the actual robot. So my handy cameraman. Yeah, so the robot is actually doing that pass that was highlighted just earlier, and we can actually see the robot pushing against the material. And if you go underneath, John, you can actually see, so in this instance, we've actually made a lot smoother increment where we're using 0.25 mils instead of the 1. So it's much, much smoother than what we've had previously. But it's really interesting to actually see from the bottom because you can actually see all of the little lines and all of the little contours that the robot's actually pushing it against. And in this instance, we've put the flashing aluminium sandwiched between 2 laser cut MDF boards. And this was so that we can actually have a clean edge when we do the actual forming. And of course, we've had to lubricate, which is what all this gucky brown stuff is. Thank you, John. But yeah, so that's the incremental sheet forming project.
Thanks so much, Amelia. And now we'll shift to Alan.
So hello, everybody. My name is Alan Burden. I'm one of the PhD candidates with the Design Robotics team at QUT. And I'm also one of the innovative manufacturing CRC scholarship holders. Over the last 3 years, my PhD research has been exploring how artisans, people that make craft and make creative products, apply their trade and interact with their tools and their technology. I wanted to see how introducing an industrial robot could change the process of making artifacts and give them potentials for new actions, which is a notion that's commonly referred to as affordances. Today, I'm going to play a video and show you one part of my research, which is the final stage of a design study, where there are 2 outcomes. The first is a system that allows artisans to interact with a robot. And the second is a piece of equipment that I designed called a drag knife, which will use by the robot to cut into 2D panels of material. So let me just play the video here. So the working title of the project is called ASAP Cutty, and it uses this drag knife, which I developed over a couple of weeks. A drag knife is not new technology. It's been used for decades in computer-controlled milling. It basically consists of a craft blade, which is quite a cheap, regular piece of equipment attached to a freely rotating spindle and drags the cutting blade through materials. I adapted a drag knife into something that could be used by this UR10 robot, much like the one that Amelia just showed before. Traditionally, it's been used for cutting out 2D patterns or templates, which my research has found is very common activity in many crafting industries, such as furniture making, garment making, and industrial pattern making. The main challenge of this project, however, was to actually create an interface that would be quickly set up and allow immediate changes to dimensions of cutting surfaces, material sizes, material thickness, and show that in a representation on the screen or a visual twin that would allow the artisan to know what was going on at all times. the main reason for doing this is to kind of lower the barrier of entry for interaction between the artisan and the robot, because if something is too difficult to use, it won't be used at all. Here I am inputting a vector into a piece of software, which is something that artisans would commonly use, like Illustrator. This is actually using Figma. There's also other vector brands which are freely available. And I can now input this using Rhino and Grasshopper plugins to see the actual toolpath of the robot and rescale it, and then start the robot and see what will happen. So this was the first test of the drag knife, cutting into some discarded corrugated cardboard. Calibrating for the depth was important. The robot is very accurate down to millimeters, so it was capable of actually being able to penetrate halfway through that material, 2 millimeter material, and actually going in 1 millimeter and etching into it perfectly. The drag knife is very slow on tight curves and circles, but moves quite quickly on straight circuits. And here it is, cutting through this corrugated cardboard quite easily. The potential for a system like this is to cut or to etch into other types of material, like Amelia mentioned, items like aluminium flashing or thin metals as well, but also possibly thin plywoods and composite plastics. And this was a proof of concept, and because it works so much on cardboard, I could probably also work on other patterns and 3D forms and shapes. The final stage of my research here is to just check the accuracy. That was the original sketched image, and this was the final cardboard piece, which was quite accurate in the end. For me, the proof of concept for how artisans could be used using a digital technology like a robot as part of their handmade technique, and a system like this could be used definitely in small scale industries and manufacturing. Thank you.
And now I'll hand over to Mugen.
When we talk about design-led manufacturing, the two ideas that we have discussed are around mass customization and the direct connection from digital to physical. So I'll be showing my research around these areas. So for mass customization, I guess the most important thing is bringing the user's interests and aspects into design. So this was the kind of image that I was talking about in relation to the industrial robotic arm. Like I said, the other potential is the connection between the digital to physical, so design to manufacture, and it really gives empowerment to the designer on material manipulation and the manufacturing processes. And also allowing cyber-physical systems such as AR, VR, and sensors to inform the outcomes, because you are in control of material manipulation and the manufacturing processes. You can actually embed sensors and other aspects into the actual planes, but at the same time use AR, VR to help in the assembly strategies as well. I'll just show a couple of projects that we have been doing as part of Design Robotics. The first one is a robotic hot wire cutting project in collaboration with UQ, School of Architecture. Basically, as part of this project, we have developed a user interface design that anyone can log in to using a web interface and design their own patterns to create complex geometries, and then those patterns can be automatically robotically cut by using a hot wire cutter attached to the end of the robot. And for the first explorations, we did a student workshop to test our workflow. This is an initial concept of that workflow where you can see the rule-based game, which is called Morpho game, where people can design their own tiles and it automatically converts into an JSON file that is then uploaded into Rhino Grasshopper to be lofted and create these three-dimensional blocks. So this work, then these blocks are sent to the robot, and the robot using a hot wire cutter cuts them out, and then it was milled. It can be built anywhere in the world. So this is kind of a showcase of what we have done as part of this research project, which our work was exhibited in Istanbul Design Biennale. And so all we did was we sent the digital code, and during 2 weeks in the Biennale, our blocks were cut and in an art gallery space, and we have created this type of like a sculptural frieze out of it. After the success of the Design Biennale, we were invited to be part of the BAD, Brisbane Art and Design Festival, which our work was exhibited in Museum of Brisbane. And this time we tested, taking feedbacks from our previous experience, we developed the code a bit more and created this suspended design element, which was representing the Brisbane River. This idea then made us question about the sustainability of the material, and we are currently working on a robotic clay cutting project, improving our interface design, looking into material research and sustainable manufacturing processes, as well as assembly strategies using AR and VR. We are designing our end effector again to hold a brand new hot wire cutter. And then we are in contact with some industry partners such as Austral Bricks to pursue this as a manufactured product. The next project that I'll talk very briefly about is the Reimagining Aged Care Furniture project that we are working on. So this project really looks at the potentials of robotic 3D printing and circular economy. So we are looking at the scrap materials of aged care furniture manufacturing, and really thinking about how we can use these in order to create a new type of a material and a smart furniture that can inform its users. So we have an industry partner again called Healthcraft, and we are looking into their manufacturing processes, mapping out the potentials of these systems and where it can be taken as a new product, and looking at 3D printing aspects of robotic 3D printing, basically. So if you have any question, you can contact me through my email. And over to you, Roland, I guess. Yeah, thanks a lot.
Thank you so much, Muge. We're a little ahead of time, and so we've got a couple of minutes for questions. I can see a couple have come through on the Q&A. Maybe we'll start with those, and then if there are any other questions, please please type them out, and then we'll get to them. So maybe, Alex, looks like there's a couple for you. The first one is around the printing speeds and the rates of the wire arc additive manufacturing.
Mm-hmm. Yes. Thanks, Mohammed, for this question. It's a good one. So in our system, we are running kind of, depending on the paths, we're printing around 5 to 10 millimeters a second while printing. I've never really measured the rate, let's say the kilograms or like gram per second or kilograms an hour, but I've found in literature that you can produce, depending also on the material that you're using, somewhat between 1 to 10 kilograms an hour. And bigger systems usually use like they have kind of a double torch. So it's not one MIG welder that feeds one single wire. Also the wire diameter affects your output if you just measure the output per hour. So if you have like 2 thick wires and basically a double torch, you can produce a higher output. The wire feed is somewhat in the range between 1 and 10 meters a second. And this is basically always coupled between the amperage you're using, voltage, the tool speed you have, kind of the tool tip orientation, the distance between the tool and the workpiece. And after all, WAAM, or like in 3D printing, you often have the problem that you have to overcome this temperature delta. So from my experience, most of production time is actually cooling time, while you have to wait for the part to cool down. So this always affects also how you measure your speed or your efficiency. If depending on the environment you're printing at, 50% of your time might be actually cooling. And there's solutions to that, right? Like water cooling and so forth. But I hope this answers your question.
Thanks for that, Alex. Perhaps another one on a related topic, either you or Amelia, perhaps you can jump in. And this is from Ahmed. Do you apply the same force for all contour lines? And what are the limitations of such a process?
So yes, currently it's open loop, it's kind of blind. The URs, or some collaborative robot, like Peter was showing before, the Franca Emica robots, like some of them have very good kind of detection of torque and force. There's also systems that you can plug between the robot. Let's assume that your arm is not a collaborative one, but a standard, maybe like a KUKA or ABB arm that doesn't measure all this doesn't have force and torque feedback. You can plug in like a device. It's called a force torque sensor that can measure all the forces and torques in several directions. And I think having this, you would be able to actually adapt according to, maybe, let's say you have a goal to maintain a certain force, because exceeding the force might mean you basically rip your material apart. That happens sometimes. But it also, I think if you had this feedback, yes, you could achieve maybe different results. But for now, yes, we are always applying the same force. And the limit at this stage, what we found so far, is the danger of ripping the material if you go too far in or too fast. But using a machine like a UR10, there's also some kind of limits of how strong this machine is and when this will actually stall out. So these machines, they don't love to necessarily do this kind of tasks, I think. So there's always like this kind of sweet spot where you look at how much energy drain the motors have, and then you can assume whether they're close to the limit or not. But maybe, I think Mia is now here. She can also answer a bit more in detail of what the URs are capable of doing.
We just, as Alex was mentioning, we just keep it consistent. It's more about being able to use the force torque sensor to be able to find a surface, as Peter sort of mentioned before, how it's all about the relative positions and knowing precisely exactly what the robot's holding and then where the pieces that you're trying to interface with. So what we can do is we can use force control in the sense that we can use that sensor to figure out where the actual tool is contacting to the surface, even if the scans don't particularly line. But in our application so far, in terms of actually trajectory following, it's all this maintaining the same force as we go along. I don't think we've had any specific application where varying the force as we follow a path has been necessary, and I can't quite think of off the top of my head what, if there would be. Would there be?
Maybe for to counteract springback, it's possible in a real-time system. So
yes.
Yeah, it's not something we've dealt with yet.
Okay, so in that instance, yeah, like definitely there is a controller that is continually checking and like updating itself. But ultimately, even with the springback solution, you would be still applying the exact same force as you go along. I think the idea of that would, yeah, you still always want the final output and like the actual following of the trajectories to always be applying the same amount of force. But the controller behind the system will definitely be like doing its own little iterative loops and trying to, yeah, counteract all of the different things.
Mia, thank you very much for that. There are a few more questions. Maybe we'll get to these at the end, but now we need to hand over to Jared Donovan and the next session on human-centered design.